Hi, this is Mrs. Vrobel. Welcome to my dining room. I'm going to be giving you a 15-minute lecture about the difference between temperature and heat. So your assignment for today is to take some notes. I have about 3 questions that I want you to answer. And when we come back to the classroom, please remember that you have a test on Chapter 14. And the following day, we'll start working on problems since we've already discussed the material that we need to worry about for Thursday. So we are going to be talking about temperature and heat. And I'm going to use my pen here. So please remember there is a difference between temperature and heat. And for right now, I want you to write down, what do you think is the difference between temperature and heat? Okay, now after you've done that, let's discuss what is temperature. So this is the challenge for a lot of students. Many people think that temperature is essentially the measure of how hot something is. And that's normal, that's a natural response, but we know from previous experience that it's something totally different. It's essentially how fast are the particles moving in an object. Now, right now I'm sitting in my dining room and my guess is the temperature in here is probably about mid to upper 60s. And that's in Fahrenheit, not Celsius. So that means that in this room, the air is essentially an average of 65 to 67 degrees Fahrenheit. Now, please remember, this means that this is the average. So we're talking about essentially the average kinetic energy. So that means if I'm in 67 degree temperature, I have some molecules that are higher than 67 degrees, and I have some molecules in this room that are lower than 67 degrees. Now, please remember, we're talking about energy, so that means that if we are adding energy, and today the high I think is going to be about 85. So if it's going to be 85 degrees Fahrenheit, something's going on to make the temperature from 67 to about 85. And we know it's going to be a sunny day for the most part. So that sun or radiant energy is going to make those molecules outside move faster than they are right now. So we're going to say that as temperature goes up, the average kinetic energy goes up. Now here I have an example of a box, and the interesting thing about this box is that one side is 90 degrees. Now there's a metal wall in between, and then here on the other side we have colder water, and notice that it's 10 degrees. Now I want you to write down in your notes, over time, what do you think is going to happen to this box? So remember, there's just a thin metal wall. We're not mixing the two, but what do you think is going to happen over time for this box? So write this down right now. Okay, pause it if you're not done. Otherwise, I'm going to move on to the next slide. Okay, here we have molecules on the left-hand side, and notice on the left-hand side, these molecules, they're moving fast. Okay, you see like the long stretchy parts of the molecules, their tails. This is just showing that the molecule is moving faster. Whereas on the other side here, they're kind of sluggish. They're slow. And these are the average kinetic energy. So in this left-hand side of the box, the average molecule is 90 degrees C. there's going to be some molecules that are moving faster than 90, some moving slower than 90. And then on the right-hand side, same thing. Some of the molecules are going to be moving faster than 10 degrees C, and others are going to be moving slower than 10 degrees C. Now, watch what happens over time. Voila! They essentially averaged out. So this thin metal wall that is between the two of them, it's essentially allowing for the temperature to equilibrate, okay? And the question is, what happened to that temperature? Well, if you had to guess, something must have occurred with that average kinetic energy. And I want you to write down, what do you think happened to that average kinetic energy? All right, if you're not done writing it down, you should pause it before you go on to the next slide. I'm going to move to the next slide here. Okay, this picture here just kind of illustrates the difference between hot and cold. Notice that something that's warm, the average kinetic energy is higher, so those molecules are moving faster, and the opposite is happening on the right-hand side where the molecules are moving slower and the average kinetic energy is colder. Now, here, I have a good question for you. So here is another statement that you need to write down about, okay? Which one requires more energy? So I have a swimming pool here, and it's 100 degrees C, and then I have a coffee cup that is 100 degrees C. So my question to you is, you want to write down which of the two requires more energy. Is it the swimming pool or the coffee cup? So go ahead and write that down. Okay, you might want to pause it if you're not finished writing it down, because I'm going to move on to the next one. Okay, this is where it gets a little more interesting. So the question is, what is heat? Now, we just learned that temperature is the average kinetic energy of a molecule. So if we have a container of gas or liquid or solid, the average kinetic energy of that substance is temperature. Now the question is, what is heat? Now we need to understand heat in order to understand energy, because they're both pretty important concepts. Well, heat is not temperature, duh, okay? We know that now. Heat is the flow of energy. So you may notice, like right now, I'm touching a tabletop and it's kind of cold. This room is cool. It's not as warm outside because it's kind of early in the morning. So my warm hand is touching the cold tabletop. My question is, what direction is the energy flowing? I want you to write this down. Is the energy flowing from the cold tabletop to my hand, or from my hand to the cold tabletop? Write this down. Okay, if you're not done writing it down, I would pause it because I'm going to move on. Heat always flows from hot to cold, and that's the bizarre thing. So if you're holding an ice cream cone, a lot of people think that the coldness of the ice cream is leaving and combining with the warm air. It's the opposite. The warm air is moving towards that cold ice cream cone. So it's kind of opposite of your thinking, and I know this is going to be a challenge for you for this chapter. So please remember, hot to cold, always. Now, the interesting thing is we don't always get an increase in temperature when heat flows from hot to cold. That's the bizarre thing. And when you look at phase diagrams, or when you look at, we have heating cooling curves, you're going to see why that happens. Okay, I think this is my last slide here. Now this is something that I'm sure you've experienced in the lab, and some of the demonstrations that I've done with like hot and cold packs. So exothermic changes. Notice that with exothermic change, we're essentially looking at changes where energy is released. Okay, so exo means outside. So whenever you see an exothermic change, that means the energy is being released by an object. Endothermic change. Okay, so endothermic change, we're essentially looking at changes where energy is absorbed. So you might notice some of the cold packs that you've come across maybe in your experiences as an athlete. Your warm body is essentially giving off heat to that cold pack. And that cold pack is essentially taking in energy. Okay. I think I'm going to pause here. So what I need you to do is to summarize your notes. Make sure that you answer the questions that I had you answer. And then tomorrow you'll show me your notes before we take the test. Thanks for watching.